I'm Ashley Abbott. My final research update is on designing a layer-by-layer biomaterial for bone regeneration. I'd like to say thanks to my sponsors listed, and a big thanks to my mentors, Dr. Svetlana Suhishvili and Jordan Brito. The goal of my project was to conduct a literature review on layer-by-layer films and the application of bone regeneration. The analysis was done with the purpose of discovering unsolved problems in the field and laying groundwork for future research in the group. To research layer-by-layer biomaterials, I analyzed papers in a few major topics to learn the fundamentals and the process of designing a biomaterial. That included the incorporation of bioactive molecules into films and the interaction of the surface with molecules. The overall question of the project is how material scientists can design materials to meet the needs of these highly specific applications. Layer-by-layer allows for control of the structure at a nanometer level for precision. The traditional electrostatic layer-by-layer process, introduced by Decker in the 90s, is based on the alternate absorption of positive and negatively charged polyelectrolytes. Polyelectrolytes, represented by red and blue, are polymers whose repeating units bear an electrolyte group. So to create a layer-by-layer film, you can start with any substrate, including a 2D plane, a complex 3D shape like an implant, nanoparticles, or substrates, and even more. Then you can carry out the layer-by-layer deposition process with oppositely charged polyelectrolytes. The process is relatively simple and can be carried out under mild conditions, which is ideal for incorporating bioactives. To modify the film, a bioactive can be incorporated into all the layers, every other layer, or just the top layer as a surface modification. There are a lot of possible surface modifications due to the versatility of the process, allowing for customization. The layer-by-layer process allows for easy change of chemical and physical properties, such as changing the wettability of the surface to increase adhesion. The total annual cost of osteoporosis fractures is predicted to grow to $95 billion by just 2040. In the last 5 years, research in layer-by-layer biomaterials for bone regeneration has increased greatly. One thing my research focused on was the interaction of the film surface with proteins, bacterial, and mammalian cells. The current issues of present solution are the low osseointegration of synthetic devices and poor bone regeneration. Osseointegration is the ability of a biomaterial to integrate itself with the natural bone. Some currently designed biomaterials also lack the ability to prevent an adverse immune response in the body or tend to accumulate bacteria. Here's a design that, in my opinion, has the potential to create solutions in bone regeneration. For a bone implant, it's important to choose a material with the correct mechanical properties, porosity, and surface roughness. As mentioned previously, layer-by-layer can be done on any substrate, and in this case, it can be done on electrospun nanofibers made out of polycaprolactone, or PCl, and polyvinyl alcohol, or PVA. In this diagram, you can see PVA as the core and PCl as the shell of the nanofibers formed by electrospinning. Chang's study is an important design of a dual growth factor system that can provide some framework for the biomaterial. Electrospinning is used to prepare nanofibrous mats or scaffolds, which are beneficial in cell attachment and are a good surface for focal adhesion proteins. They also have high porosity, mechanical stiffness, and gradual degradation, which is beneficial in a bone scaffold. PCl is highly utilized in bone regeneration because it's readily available, biocompatible, and has long biodegradability time in the body. Silk fibroin, or SF, a biopolymer, can be blended with PCl to tune degradation time. PVA can be used as a core of the architecture due to its biocompatibility, availability, its mechanical stability, and flexibility. It's chemically stable and it's commonly used in electrospinning, and it was also able to encapsulate a protein in studies. In this middle figure, you can see a cross-section of a human bone and its 3D interconnected porous structure. The figure on the right shows nanofibers that mimic the porosity of bone and increase adhesion of cells to promote growth. Interconnectivity of the pores can also promote adhesion and spreading of cells. Nanofiber scaffolds actually present more binding sites to cell membrane receptors, improving cell attachment as shown in the bottom part of the figure. To modify these nanofibers for even better adhesion, layer by layer is used to prevent an immune response and make the surface more hydrophilic to promote better interaction and adhesion with cells in the body. Layer by layer modifies the surface of the biopolymers and changes the physical and chemical properties of the scaffold. So in the core, we would use PVA, while in the shell, we would use a PCl-SF blend. Here's a cross-section of what the morphology would look like. A bioactive organic layer, like chitosan, is commonly added to the surface of a synthetic biomaterial to reduce the time for osseointegration, increase cell growth, and improve the hydrophilicity. Often hydrophilic surfaces are favorable for initial attachment and spreading of fibroblasts, which are used in bone healing. Layer by layer can be used to change the properties of the nanofiber by surface modification. Positive chitosan in red, shown here, and the navy negative layer are used by layer to modify this scaffold. Another commonly utilized method to improve the biocompatibility is incorporating PEG. PEG can resist protein absorption, and these short chains could be incorporated throughout the whole nanofiber. These surface modifications allow for a more biocompatible and hydrophilic scaffold. Another very commonly utilized method for modification is incorporation of bioactives like proteins. Growth factors are a type of protein that have been incorporated into these designs. As shown in the cross-section here, CTGF was incorporated via layer by layer on the outside, and BMP2 was incorporated into the shell and the PBA solution. This is in order to model the natural process of bone healing, because BMP2 is slowly released over a 1 to 3 month period of healing, while CTGF is released in a burst release quickly in only the beginning stages. So this is able to better model the natural process than some previous designs that suffer burst release of BMP2. A dual growth factor system has also been shown to be more effective because it promotes both blood vessel formation and the bone healing process, while a single growth factor might only help with one of those processes. This new research could be further modified to better improve its ability. Bacterial infection is a common problem with implants that are placed inside the body. If a biofilm of bacteria forms, the implant is likely to fail, and that's a large issue. So we commonly use antibacterial agents to slowly release from the design to prevent bacterial adhesion. This is beneficial if done correctly, however, it has some drawbacks. They include possibly creating more resistant strains of bacteria or inactivity of the agent. But it has been shown that vancomycin, an antibiotic, can be incorporated into chitosan. I propose that the antibiotic be incorporated into this design along with each layer of chitosan. Another option for preventing bacterial adhesion is the incorporation of nanoparticles. Silver nanoparticles are known for having antibacterial properties. However, they're toxic at high concentrations and can suffer from inactivity when incorporated into layer by layer. As you can see in this picture, the vancomycin is added along with each layer of chitosan. And now that I've talked about a few successful design aspects, I will talk about more of the bone regeneration design. As shown in the figure, a nanofibrous mat is formed from the process of electrospinning, and the surface of the fibers can be further modified using layer by layer. To test the biomaterial, the interaction of the scaffold with cells and proteins needs to be analyzed. In the body, proteins almost immediately interact with the surface, while cells and bacteria come soon after. In bone tissue engineering, some protein adhesion is desired for cell proliferation. It is believed that the balance between proteins absorbed to the surface and cell adhesion correlate. There are both adhesion-promoting proteins like fibronectin and adhesion-inhibiting proteins like albumin, so it's desired for adhesion-promoting proteins like albumin to absorb at a higher concentration. Then, cell adhesion is tested to see how well cells will adhere and grow on the surface. Also, cell studies determine the biocompatibility of a material by seeing how many cells are alive or dead. As mentioned earlier, bacterial adhesion is not ideal and should be prevented to avoid implant failure. A test using both gram-negative and gram-positive bacteria could be effective. It would be interesting to test varying amount of bilayers deposited using layer-by-layer process to see how the change in number of bilayers would affect adhesion behavior. Lastly, PEG can be grafted onto the surface with varying degrees of substitution. If the degree of substitution was varied, the adhesion behavior and interactions of molecules could change. While my design considers a lot of aspects, there are still some disadvantages. It might be expensive due to protein incorporation. The design is complex, so it could be hard to fabricate. However, overall, I think this design has potential to solve problems that prevent progress in this field. Since most of this research is still in the fundamental stage, I think it is important to prove the concept could be achieved first. Problems still faced with bone regeneration are low integration of the devices into the bone and poor bone regeneration. After researching the layer-by-layer process utilized in biomedical applications, I think layer-by-layer and this design specifically could lead to further innovations. Layer-by-layer provides a relatively easy technique for incorporating bioactives, which is beneficial in bone regeneration, tissue engineering, and many other applications. The dual growth factor system allows for a more closely modeled process to the natural bone healing process. Layer by layer also provides an easier way to modify materials that might not necessarily meet every criteria. For example, in this case, PCl is a great scaffold material, but the hydrophilic polymers added to the surface make it more ideal for cells to adhere. This design was based on recent innovations found in literature and addressed issues of previous designs that require improvement. The layer-by-layer process will allow for further innovation in the field of bone tissue engineering and other biomedically relevant applications. Thank you for watching.